Hello everyone and welcome back to my class. In this video, we are going to continue using other error correcting codes and how they are used by solving the given problems. Aside from the parity check method, the repetition code is also one of the basic error correcting codes used to repeat a bit several times. When a bit is to be transmitted, it is instead transmitted multiple times and compared to see if there are any errors detected and to be corrected. This is used by taking k bits, then repeating it 2r plus 1 times, and r is a positive fixed integer. Now let's move on to answer the first example. Suppose that the source of encoded message is 101. If r is equals to 3, what will be the message? So in order to use the repetition code, we will first compute k, and the formula is 2r plus 1. And since r is equals to 3, we will insert 3 to this equation and solve for k. As a result, k is equals to 7. Now that we solve for k, the next step is to repeat the code word by k or by 7, which means that 101 will be repeated 7 times. And as a result, this is the final answer. And how is it repeated 7 times is 101, 101, 101, 101, 101, 101, 101, which means they are repeated 7 times. So in this case, suppose that the source encoded message is 01. If r is equals to 2, what will be the message? The same goes for set number 1, where we first find k along with its solution, where we insert r to this equation and we got k equals 5. Now we will use this 5 to repeat this message by 5 times. And the answer is this, where 0, 1, 2, 3, 4, 5. Just to take note, R is represents as a block bit where the where it this divide the code word based on the number of bits in division. So in this case, what if the noise affected the message in the given example below and the message decoded was 000 110 001, I mean 011 111 101 101 001. Determine the correct source encoded if r is equals to 3. So we are in the first two given examples, we were told to encode the source encoded word. But in this case, we are supposed to find the source encoded word by using the message decoded. What you're gonna do over here is to use this number to divide this decoded word by 3, where each division have 3 bits. So the result will be like this. After doing this process, you will now actually find the first, the second, and the third digit. Since r is equals to 3, this means that the source encoded is actually 3 bits. And we're going to, in the first digit, which represents all divisions that has, how am I supposed to explain this? Every division of this code word. In other words, we will actually count the number of ones and zeros in every first digit of the division. So in the first digit, there's about 2 zeros and 4 ones. As for the second digit, there's about 4 zeros and 3 ones. And as for the last digit, there are 5 ones and 2 zeros. After you figure out the numbers of ones and zeros on the first, second, and third digit, you will now find the dominant of between the ones and zeros of each digit. So for the first digit, 1 dominates 0. So because there are 4 ones and 2 zeros. Which means your first digit is 1. As for the second digit, it is 0. And for the third digit, it is 1. So your final answer will become 101. This is your correct source encoded. We move on now to the Hamming distance. This is used to compare two code words to determine whether there is a number of bit positions that differ. So this compares two code words or two bit strings where whether there is an error between them by determining the number of bit positions that differ. And so these two code words represents A and B and are denoted to this equation. So let's say for example, where there are two code words, which is 1101, 1001, and 1001, 1101. In this case, we are going to denote these two code words into this equation, where A is this code word and B is this code word. After you denote them, you will now determine the number of bit positions that differ. So in this case, we start from the first digit, 1, 1, 1, 0. Now that's 1, 0, 0, 1, 1, 1, 1, 0, 1. That's 2, 0, 0, and 1, 1. So in the end, the Hamming distance between the two code words is 2. But what if there are 4 code words that we needed to solve? In this case, you're gonna have to check the Hamming distance between each and every code word between one another. And in this case, they are denoted to this equation. So in the end, you will see that the first pair, the first pair of code words is 1, 3, 2, 2, 1, and 1. And that's your final answer. But there's one more thing. In the Hamming distance, there's also known as the minimum Hamming distance, which represents that this means that there should be, among all the Hamming distance, there should be at least the minimum Hamming distance. And in this case, the first, fifth, and sixth